permutations and so on. So let me begin by recalling some of the standard facts about permutations. So for example, the number of permutations of n distinct objects. So the number of permutations of n distinct, meaning they're labeled objects, they're all different from each other, 1 to n. As you know, this is of course n factorial. And of course, this is the cardinality of the symmetric group of that order. So in terms of groups, maybe the correct way to think about it is to say that's the cardinality of the symmetric group. And so I'm sure you've seen, I mean, by now, of course, you must have seen proofs of this and so on. And the other operation is that of combinations. So the number of combinations of R out of n objects, of R objects among n distinct objects labeled 1 through n. So in other words, there's a number of ways of picking R elements out of these n, and that is what we call NCR. Okay. So this is n factorial by R factorial n minus R factorial. And here R is a number between 0 and n. And so this is, so by the way, again, another standard notation for this is to say n choose R, write it within brackets in this way. So this is the number of combinations. And so again, maybe does someone want to give me a quick argument or proof for why this is the right number of combinations? Just unmute and speak. So why is NCR equal to this particular ratio of factorials?
Sir, the formula for NPR is the n factorial upon n minus R factorial.
Okay.
Okay. And suppose that if I'm selecting the R elements, in permutations, we are counting that elements R factorial times.
Okay, fine. So you want to go via NPR, that makes sense. So what is NPR? This is the number of permutations of R objects among these n. So you first pick any R objects and you arrange them in a line in all possible ways. So 1, 2, 3 till n. And the number of ways of doing this is so sort of the usual counting rule. There are R positions to be filled. And each position, so the first position has all n choices. The next position has only n minus 1 choices because you have already chosen something in the first position and so on. So n minus 2, etc. till n minus R plus 1. Right? So that is exactly, can be rewritten as n factorial by, I mean, this product n into n minus 1 into n minus 2 till n minus R plus 1 is exactly this. But the point is now that when you want to only choose R objects and you don't exactly care about in what order they're arranged, so it's as if I just take these R objects and sort of just put them in a bag. I don't care how they're arranged. So each such permutation of these R objects, if I only care about the objects themselves, each such combination will occur R factorial times. Right? I will get the same set of R objects occurring in R factorial different orders. There are those many permutations. So that's the extent of overcounting. So the argument here is, this is just, you take all possible permutations of n objects, but then each combination or each choice of R objects is being overcounted by a factor of R factorial. So you divide by that overcounting factor. Okay. Yeah. Sounds good. Yes. Now, so let's go on to the So here's an interesting corollary of this this fact here, which is that if I take so observe NCR or choose R is, you can also rewrite it as as NPR divided by R factorial. So let me write it in that way. Right. So now here's here's an interesting corollary that if you take any R consecutive numbers, any R consecutive natural numbers, the product of any R consecutive natural numbers is always a multiple of R factorial. So somewhat surprising fact if we hadn't stated it right after this discussion of combinations. Can anyone see why this must be true? It doesn't matter which R consecutive numbers you pick, just anywhere in the number line, any natural numbers are consecutive.
We are having R consecutive numbers.
Sorry?
In NCR formula, we are having R consecutive numbers.
Okay, so why does that prove?
Yeah.
So for example, let me say, so let me just give you R consecutive numbers. So suppose I give you, so let's pick some natural number A and let's multiply. So let's start with some natural number A and look at A into A plus 1 into A plus 2. So I'll take R consecutive numbers, A plus, so maybe let's do A plus 1, A plus 2, A plus R. That's a sequence of R consecutive numbers, right? So why is this divisible by R factorial? So maybe I will put, yeah, okay, well, let's keep it like this. So I want to start A, I also want to allow A equals 1. So let me maybe do this, A plus R minus 1. So why is this divisible by R factorial? If I divide by R factorial, so what you were saying was along the right line. So if I take this numerator, this product, and divide it by R factorial, then it's actually some NCR in disguise. Right? For what value of n is this equal to NCR?
N equal to A plus R.
N equals A plus R?
Yes.
I just modified it to A plus R minus 1. So if I write it in this way, so if you sort of look at what this formula is, the largest number is n, right? So now I'm just rewriting it in the other order. So this is the largest number among these R numbers, right? So actually this product is nothing but this largest number, which is A plus R minus 1 CR. Okay. I mean, you can just see from the formula because the numerator is exactly R consecutive numbers from n downwards. And that's exactly what this is. You start at A plus R minus 1 and go downwards. So the point is, this, however, is known to be a natural number, right? Why is this a natural number? This is always a natural number. I mean, or 0 could, of course, be 0 as well. Why is this particular number always a natural number or 0? Well, one way of saying it is because it has a certain interpretation, right? So we just said what this particular quantity is, it counts something. The fact that it counts something implies it is a natural number, right? It is the number of combinations. So this is definitely a natural number, or it could be 0. And so what that shows is that this fraction, if you divide this numerator by R factorial, the resulting fraction is a natural number, which means the numerator is divisible by R factorial. Okay, so that's just a little corollary of this formula. Now, so of course you must have seen many other properties of NCR and so on. So here are well, for one thing, the sum of all the NCRs, R goes from 0 to N, gives us 2 power N. This is for all N greater than or equal to 1. If you add up all the number of ways of choosing R objects for a fixed value of N, it just gives you 2 power N, right? So how does one see this formula? What's the proof of this?
Use the binomial formula 1 plus x whole power n.
Okay.
Substitute x equal to 1. Okay.
So there is this binomial formula 1 plus x whole power n equals summation NCR x power r, right? R equals 0 to 1. So this is the traditional way in which we prove a formula like this. But of course, there is also now a combinatorial or a bijective way of proving this.
Left-hand side is representing the number of subsets, and the right-hand side is also representing the same.
Okay, fine, great. So think of it as follows. So I have n objects or a subset. Let's say I have a set. So I have a set containing the numbers 1 through n. Now, what does the right? Let's start with the left-hand side. What does the left-hand side tell you? N choose R is the number of R element subsets of this set. Right? So for each R, so let's think of it like this. N choose R is nothing but the number of ways of choosing R objects. So that means it's the number of R element subsets of this set 1 through n. Okay, but now you're summing over all the R's. So what does that mean? Therefore, the left-hand side is just the total number of subsets, because you are allowing all possible cardinalities. You don't need to fix a given value of X, a given value of R. So this is nothing but the total number of subsets, including the 0 element subset and the n element subset, right? So empty set, whole set, everything's allowed. But total number of subsets you can count differently, right? So this we know. This is just how does one count the total number of subsets? There are totally n elements, and you can, for each element, you can either choose it to be in the subset. You can either make it on or off. Right? On means you choose it in the subset. Off means you don't choose it. So the total number of subsets, on the other hand, can directly be counted to be 2 power n. Right? So this argument is sort of what we sometimes call a bijective proof, because what we're doing is establishing on the left-hand side, we are saying that the left-hand side counts certain number of objects, objects of a certain kind. In this case, it's subsets of the given set. The right-hand side also counts some objects of a given kind. And then you explicitly show that these two objects that are counted have the same size. Okay, so which is what we have done in this case. In this case, it's even simpler because both are really counting the same set of objects, but in 2 different ways. That's all. Okay, so that's one property. So the other fact, of course, is the Pascal's triangle. So you can arrange the coefficients NCR as follows. So you put 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, and so on. Etc. Where the entry is in a given row. So in the nth row, you put the numbers NC0, NC1 till NCN. So here, for example, n equals 4. In the 4th row, I put 1, 4, 6, 4, 1. Okay, the top is thought of as the 0th row of the Pascal's triangle. Okay, and you've probably seen this sort of very nice fact about the Pascal's triangle. How does one get the next row from the previous row of the triangle? You don't actually need to know all the values of the binomial coefficients. You can, if you know a given row, you work out the next row from it. Anyone remember the rule? So I'm asking, how do I get the 5th row of the triangle? Meaning, how do I find the coefficients 5 choose 0, 5 choose 1, and so on? From the
adding the elements.
Sorry, what?
Adding the 2 elements, previous 2 elements.
Adding the previous. Correct. For example, 5.
4 and 6
1
will give 10.
4 and 6 will give 10. 6 and 4 is 10. 4 and 1 is 5. So the last ones are thought of as 1 and 0. So you imagine there are zeros sitting outside there, and so on, right? So 4 again is 1 plus 3, 6 is 3 plus 3, 3 plus 1, similarly is 1 and 0, right? So the elements in the subset, that's sort of why this is drawn in this manner. Each successive row elements are just the sums of the two things above it. It sits in the middle of those two guys, right? The way we draw this pattern. Okay, so this property is just the following, that if I take the any given element of let's say n is 4 in this case. So in the n plus 1th row, if you take the r plus 1th element, meaning the r plus 1th coefficient. So this is, for example, this is like 5c2. Then it will be a sum of two things. One of them is 4c2, which is this, and 4c1. Okay, so 5c2 is a sum of 4c2 and 4c1. So it's, in general, the pattern becomes this. Right? So the two things in the previous row which add up to give you the next guy are exactly NCR and NCR plus 1. Okay, so so that's the property we want. So let's just keep this. So how does one prove this fact? NCR plus 1 is n plus 1 CR plus 1 is NCR plus 1 plus NCR, and this is valid for all n greater than or equal to 0. Let's say R between 0 and n. How does one prove this fact?
The left-hand side says that we are selecting the R plus 1 person among n plus 1 person.
Okay, very good.
And in the right-hand side, in the first term, I'm ignoring one particular person.
Okay.
So there are no n persons, and from n person, I'm selecting the committee of R plus 1.
Okay, so there's a number of ways. Okay, right. Sure. And the next term?
The second term, in the second term, I'm including one person.
Correct.
And now only n persons are there. And I have to select now remaining R persons. So that can be possible by n combination of R ways.
Okay, wonderful. Thank you. So it's like saying you want to choose a cricket team from a collection of possible players, right? So there are whatever 15 players, out of which you must choose 11. So the way you do it is you pick one person first, a particular person. Okay, so you have some particular cricketer in mind, and then you say, okay, let me see how many teams I can form if I choose that particular person. Okay, so first choose that person, and then you choose the remaining team. Okay, so how does that work? Well, that's this NCR. Okay, what does this say? This is the number of teams, or the number of let's write it this way, number of ways of choosing a team of R plus 1 people, R plus 1 persons, from a total available set of n plus 1 persons. Okay, so this is the number of teams in which a particular person, let's call him A is chosen. Okay, and now the other is, well, these are, this is now counting the number of teams where A is not chosen. Okay, why is that? Because you're not choosing A, which means that you still have to choose R plus 1 people. The full team has to be chosen, but you only have n people remaining, from which you must choose the remaining R plus 1 people. In this first choice, you have already chosen A, so there are n people remaining, but from those n, you only have to choose the remaining R people, because you already chosen one person. Okay, and now observe that in any team, either that person A appears or that person A does not appear, right? So you have sort of split the possibilities into two, and those are exactly the two possibilities that the right-hand side calculates. Of course, one can just prove this simply by writing out the definition. You can just write all the factorials out and just manipulate the fractions and so on. But this sort of bijective proof is sometimes very valuable. It gives you some insight into what lies behind these identities. Okay, and so on. There are many identities that the binomial coefficients satisfy, and quite a number of them can actually be proved in a similar fashion. You can just construct some nice bijections. Okay, any questions on this? Okay, let me go ahead. So there is also this other type of, sorry, what number was I on? Okay, it's called 3. So, there is also permutations in which repetitions can occur. So this is the other. So you've probably seen problems like this. How many different combinations? Oh, sorry, how many different permutations can you form from using some letters? I don't know. So for example, let's say 2 A's and B's. Maybe I'll just use zeros and ones. So here's a question: how many permutations are there of the string? So by string, I just mean a word here with zeros and ones. So suppose I put 0, 1, 0, 0, 1, 1, 3 zeros and 3 ones. Okay. So here's a string. We'll put 4 with 3 zeros and 4 ones. And I want to know in how many different ways can I permute all the letters and get different words. Okay, I only want to get different strings, not I want to think of all the zeros and all the ones as being the same. So how does one do this?
7 factorial upon 3 factorial into 4 factorial.
Okay, so this number in this particular example is there are totally 7 numbers or 7 objects. So you can permute those 7 in 7 factorial ways, but many different permutations will give rise to the same word because the zeros and the ones are indistinguishable. So how many different permutations will give you the same thing? So imagine so one way to argue here is to say, let's put some labels on the zeros. So this is called 0, 1, 0, 2, and 0, 3. Okay, so now I can distinguish them because I put labels on top. Similarly, this is 1, 1. So this is the second one, this is the third one, this is the fourth one. Okay. So I put labels on the ones and the zeros so that now I can distinguish those letters. Now I imagine permuting these 7 distinguishable letters, but the 3 zeros that I have, 0, 1, 0, 2, and 0, 3, any permutation of those 3 doesn't affect the final word. Similarly, any permutation of the 4 ones in my word does not affect my final answer. So the extent of overcounting, you're overcounting by a factor of 3 factorial, 4 factorial. Okay, so that's exactly the number of permutations with repetitions. And so of course, this sort of thing works in greater generality. You can also do things like if I had 3 letters, for example, 0, 1, and 2, and if I had, say, 3 zeros, 4 ones, and some number of 2s, you can use the same argument. You can say, okay, now I want to know how many permutations of 9 letters there are. 3 plus 4, 7 plus 2 is 9. So I take 9 factorial permutations, but I divide by my overcounting factor, which is I can permute the 3 zeros among themselves, the 4 ones among themselves, and the 2 2s among themselves. Okay, so this is 9 factorial by 3 factorial, 4 factorial, 2 factorial. So this will be the number of distinct permutations. So this is the number of permutations of the word 0, 0, 0, 1, 1, 1, 1. Okay. So here's a little thing to observe. This number 7 factorial by 3 factorial, 4 factorial that I obtained in the previous problem is actually just 7C3. Okay. Does anyone see any reason why this, we gave one reasoning for why it is 7 factorial, 3 factorial, 4 factorial, but that answer turns out to be just the number of combinations. It's 7C3. Can one see it more directly that it should be this number? Can anyone come up with the reason why this should have been 7C3 in the first place? So why is the number of permutations of 3 ones and 4 ones and 3 zeros? Why is it just 7 choose 3? How is it a combinations problem?
We can think like this. Suppose there are 9 places.
Let's do the earlier one, 7C3. Yeah, there are 7 places. Okay, 3, 4, 5, 6, 7.
And okay, we have to fix 4 ones.
Okay, so you
number of possible position for 1 is the 7 combination 4.
Absolutely. So now the thing to do is to label the places. Let's call the places 1, 2, 3, 4, 5, 6, 7. And now what we are doing is out of these 7 places, you choose, let's say 3 places, 7 choose 3. I have to choose 3 places where I will put zeros. Okay, so let me say, suppose I say, okay, I put 0 in the 2nd place, the 4th place, and the 7th place. So I have chosen those 3 numbers. So in 2, 4, and 7, I'll put zeros. And then automatically that fixes where the ones appear, right? The remaining positions I must have ones. Okay. So in this case, it's very clear that this is a binomial coefficient for this reason. And by sort of a similar token, what we have here is what's usually called a multinomial coefficient. So this number here is usually called the multinomial coefficient. Sort of it's a generalization, if you will, of binomial coefficients, and often the notation is this: we write 9, 3, 4, 2. It's just like the earlier one. I mean, the C notation is not particularly conducive to multinomials. That works nicely only when you have 2 things. N choose R, NCR is okay. But for multinomial coefficients, the standard notation is to use the other one with brackets. So 7 choose 3 is written like this, 9 choose 3, 4, 2 is written in this way. Okay, and multinomial coefficients are actually related to binomial coefficients in much the same way. So recall, how do you get binomial coefficients from the binomial theorem, right? If I take x plus y power n, then as we just said, it's exactly r goes from 0 to n, NCR, x power r. X power n minus r, y power r, let's say. So that's the binomial theorem where the binomial coefficients are here. And so, of course, as expected, if I had 3 variables, x, y, and z, and I raise the whole thing to the n, okay? And in general now, what will the powers look like? It's some power of x, some power of y, some power of z. It's going to expand out like that if you just rewrite the whole thing. But what do you know about these 3 powers? Any relation amongst them?
The sum is n.
The sum is always n. Right? If you just try expanding x plus y plus z the whole power n. I mean, one way of thinking about this is x plus y plus z into x plus y plus z into x plus y plus z and so on. I have n such brackets. So from each bracket, I can either take an x or a y or a z as a contribution, right? But when I take one such term from everything, the final monomial that I'm forming will look like x to the a, y to the b, z to the c, but the total number of terms is actually n, which means the total x's I chose plus the y's I chose plus the z's I chose must have been the number of brackets that were there originally. So that's n. And the coefficient now is exactly the multinomial coefficient that I told you about. N choose ABC. Okay, so this is not too hard to put. So in fact, the problem is really the same. It's like asking, I mean, the previous way in which I framed it, I have 9, I want to form a word with 9 letters total, in which 3 are zeros, 4 are ones, and 2 are twos, right? I asked for the answer to that problem and we reasoned that it is this number here. The very same problem can be rephrased as follows. So for example, if I take x plus y plus z power 9 and I ask, okay, when I expand it, I know I will get many coefficients, but what is the coefficient of, let's see, 0 is like x for me, x cubed y power 4 z square. So I ask, when I expand, what coefficient will come in front of this term, x cubed y power 4 z square? And the answer is exactly the thing that I just told you. If you think about how do you expand such a bracket, how do you expand something power n, you expand it as follows. You get many words when you expand this bracket. The way you get it is from the first bracket. So imagine I put one place for each bracket. It's like, how do I form a word? So I should say, okay, we'll just do this. So think of 1 to n as my different brackets. Okay, this is the first bracket, second bracket, n bracket. From each bracket, I have to pull out one of the letters, x, y, or z. So maybe from the first bracket, I pulled out x. From the second bracket, y, x again, maybe then z, etc., etc. Right? From each bracket, I pulled out a thing like this. So this expansion will therefore give me, so what will this expansion finally give me? It will be a sum of many such words. So it's actually a sum of things like x, y, x, z, etc., etc. This is one word. Maybe I'll get many such, etc., etc. Okay, I'm going to get all possible words in the letters x, y, z with the total of how many were n letters, with total n letters. Okay, now I'm just writing the word in the same order. Okay, but of course we know x, y, x is like x square y. I can put the x's together, the y's together, and the z's together finally. But for now, let's just write it in the same order so that we remember from the first bracket what we pulled out, from the second bracket what we pulled out, and so on. Okay. So now the question we are asking here is saying, after we do this full expansion, you write out every possible word that you will get. So by the way, how many words will we get when we expand this out fully? So let me ask that question as well. So if you expand it on expanding and writing it as a sum of various words, how many words will I get on the right hand side?
Three power n.
3 power n, absolutely. Okay. Why is this? Because from the first bracket, I have 3 possible letters, x or y or z, right? So those words that I have, I mean, the way I wrote it, there are n brackets, 1 to n. From the first bracket, there are 3 possible alphabets that I can pick from the first bracket, 3 possible alphabets from the second bracket, and so on. So it's 3 into 3 into 3 n times. So there are 3 power n total brackets that I will get. Okay. And but then the question I'm asking here is, after I expand these 3 power n words, and then I collect coefficients, right? Many of these words will actually be the same monomial, right? Because if I had x, x, y, z, for example, this or x, y, x, z, these are both finally the same monomial, right? They are x square, y, z. Why is this? Because the variables x, y, and z are commuting variables. I mean, we're thinking of them as just being polynomials in these commuting variables. Okay, so finally, after expanding and collecting coefficients, we are asking what will be the coefficient of x cubed y power 4 z square. Okay, another way of saying it is how many different words would appear in this expansion which contain 3 x's, 4 y's, and 2 z's, right? Because each such word I can, put the x's, y's, and z's together to form this monomial. Okay, so is this clear? So finally, when I'm saying, so the coefficient of any given monomial x power a, y power b, z power c in this expansion is just the answer to the following combinatorial problem is just the number of words among these 3 power n words, number of words in x, y, z of length n with a x's, b y's, and c z's. And that is exactly as we just argued. It's nothing but n factorial by a factorial, b factorial, c factorial. Okay, why? What's the argument? You again arrange all the n words, but you can, among the x's, you can permute among the y's, and you can permute among the z's. And so this is the multinomial coefficient. Okay. And so, I mean, you don't need to stop at 3. Similarly, you have multinomial coefficients for any n. You can also talk about, 15, choose 3, 1, 7. Let's see, how much is that? 10 plus 1, 11, 4. 15, choose 3, 1, 7, 4. So this is the multinomial coefficient, which is what will happen when you take 4 variables x plus y plus z plus w and raise it to the power 15. Then the coefficient of x cubed y power 1, z power 7, w power 4 in the answer is exactly this multinomial coefficient. Okay, so this is the natural generalization of the binomial coefficients. And so here's an easy question. So suppose I take, say, these so-called trinomial coefficients, if you wish, take n, choose a, b, c. Okay, or all the different possible choices of A, B, and C. So A, B, C, all choices. Such that, I mean, I have to take all ordered triples A, B, C such that A plus B plus C adds up to n. Okay, all of them have to be greater than or equal to 0. If I add all these trinomial coefficients together, what do you expect to get?
3 power n.
3 power n. Why? Why do you say that?
Numbers we are having. So each place we are having 3 choices.
What? So you're okay. So you're just using this theorem. Are you using this? You're just putting 1 for x, y, and z, or
Yes,
I mean, or I guess what you're saying is the combinatorial argument, right? That there are totally 3 power n terms in the answer, and if you just add these numbers up, the number of choices. So this is like the argument we gave for why the sum of the binomial coefficients is 2 power n. Okay, yeah, sounds good. So I mean, you can argue in whichever way you want. So this is the other argument which works in the binomial case. You can put all variables equal to 1. So similarly here, when you do that, the left-hand side is 3 power n. So and so on, 4 power n, 5 power n, whatever. When you add up the corresponding multinomial coefficients, you get that appropriate. Okay, so this is the sort of permutations in which some objects can repeat, for example. And the other such thing is combinations with repetitions, just like permutations with repetitions. We can also look at combinations with repetitions. And what is the, let's start with an actual formulation of a question. We say I have a large collection, from a large collection of 1 rupee, 2 rupees, 5 rupees, and 10 rupee coins. Okay. How many ways are there of choosing R coins? I mean, you can give some particular number also for R. So let's say 4 coins. I mean, I don't want this 4 and that 4 to be the same. Let's say 3 coins. So I want to choose 3 coins with these denominations 1, 2, 5, and 10. Okay, but those coins themselves are available in plenty. Imagine you're in a bank in which they have any number of these coins, but you just want to form a combination of 3 out of these coins. Question is, how many different combinations can one form? So, I mean, the first question is it 4 choose 3?
No.
Okay. So it's not 4 choose 3. That's the very first thing that we have to be aware and alert about. This is not the same problem as the previous one. It's not a combinations problem. See, what would 4 choose 3 be an answer to? It would be, suppose I had exactly one 1 rupee coin. I only have 4 coins with me. Just one 1 rupee coin, one 2 rupee coin, one 5 rupee coin, and one 10 rupee coin. Right? 4 distinct objects. Out of these 4, I have to choose 3. Then that's 4 choose 3, 4C3, right? But here, that's not what we're saying. We're saying we have any number of 1 rupee coins available, any number of 2 rupees, and so on. And finally, you are supposed to choose only 3 coins. So, for example, your choices could look like this. All 3 coins you can take as 1 rupee. All 3 coins can be 2 rupees, and so on. So, you can take repetitions here. Or you can take 2 1 rupee coins, 1 2 rupee coin, 2 1 rupee coins, 1 5 rupee, and so on. You can take all 3 distinct if you want. Right? So this is not the same as the usual combinations problem. This is the combinations with repetitions problem. But the question is, how does one, how does then formulate this in a way in which we can solve it?
Can we say that number of non-negative solutions of the equation x1 plus x2 plus x3 plus x4 is equal to 3?
Sounds good. Yes, wonderful. Yeah, okay, this is the same as, okay, so let's reformulate the problem. Sometimes that helps us. This is the same as asking for the number of solutions to the following equation. So there are 4 variables now. Let's call them x1, x2, x5, and x10. Okay, where x1 means how many 1 rupee coins there are in your choice. Okay, x2 will be the number of 2 rupee coins, number of 5 rupee coins, and number of 10 rupee coins that you choose. And the total number of coins is supposed to be 3. Okay, but there are some conditions. All the xi's, all the variables have to be non-negative integers. They have to be integers that are greater than or equal to 0. Right? So I'm looking for the number of non-negative integer solutions to these equations. Okay, wonderful. So that's so I hope everyone's convinced that this is just an equivalent formulation of the problem. So here, to convert between this and that, if you have a way of choosing, then from that choice, you will just make, so for example, let's take this guy, 115. This choice corresponds to x1 is 2 because I have chosen 2 1 rupee coins. x2 is 0 because I have not chosen any. x5 is 1, that is 1 5 rupee coin. x10 is 0 because there are no 10 rupee coins. So this is the solution. 2 0 1 0 corresponds to this choice, taking 2 1 rupee coins, 1 5 rupee coin, and not taking coins of the other denominations. Okay, wonderful. So how does one solve this problem then?
Corresponding to addition sign, I am taking the one vertical line.
Okay,
If there
fine.
are the 3 additional sign, so I am taking first of all 3 vertical line.
Okay, fine. And what do you want to do with the vertical lines?
Okay, now after that, if we are selecting the 2 1 rupee coin and 1 5 rupee coin, then I can represent this selection as like this. 0 0. First of all, sir, please draw 3 vertical lines.
Oh, okay. So you just want me to draw vertical lines in place of the pluses. So
yeah.
let me draw 3 vertical lines there. Okay, sounds good. Now,
if I'm taking the selection 1 1 5, so corresponding to this 2 1 1.
Yeah.
On the left of first line, I am putting the 0 0.
On the left of the first line, you put a 0 0. Ah, okay. You put 2 dots, let's say. Okay.
Yeah, 2 dots.
Ah, okay, fine.
Okay. Now suppose my second box is for 2. It is empty.
It's empty. So don't put anything.
Box, I'm putting only 1 dot. And to the right of that line, I'm not putting anything.
Okay, fine.
So corresponding to the selection 115, this is my pictorial representation.
Okay, wonderful. Okay, great.
And
so
I'm permitting any of these symbols, we will get the one possible solution.
Okay, sounds good. Okay, great. Thank you. I understood what you wanted to say. So, so what is being proposed is the following: that one can encode these choices. So there is sort of an encoding. So, for example, imagine I picked 2 1 rupee coins and 1 5 rupee coin. So we will represent this in a pictorial fashion. So here is a pictorial encoding of this choice as follows. So, so first there are 4 denominations. So first let's draw these sort of vertical dividing lines, dividers. So there are 3 dividers because there are 4 different categories. So you take 3 dividers, and now the first category, this thing here, will represent the number of 1 rupee coins that you pick. Okay, so this is the number of 2 rupee coins, this is the number of 5 rupee coins, and this is the number of 10 rupee coins. So now, if you chose 2 5 rupee coins, you put 2 dots there, because there are, 2 1 rupee coins, you put 2 dots. Because you choose 1 5 rupee coin, you put a single dot there. And the other 2 spaces for the 2 rupees and the 10 rupee spaces, there you don't choose any. So therefore, you don't put any dots. Okay. So finally, what this means is that, so what's the final pictorial encoding of this choice 115? It's 2 dots followed by a divider, followed by another divider, followed by 1 more dot, followed by 1 divider. Okay. So this is now, what does this picture have? It has 3 dots because I'm supposed to pick 3 coins total. And I have 3 dividers because there are 4 categories which have, so if you have 4 categories, there will be 3 dividers. Okay, so let's do one more maybe to see how this sort of pictorial encoding works. So if suppose I had chosen a 1 rupee coin, a 5 rupee coin, and a 10 rupee coin, this was my choice of the 3 coins, then I will represent it as follows. So here's what I know. I have chosen 3 coins, so my picture should certainly have 3 dots total. Right? Because totally there are, for each coin that I have chosen, I'm putting a dot. The question is, in which divider does this this dot appear? So here I have chosen only 1 rupee coin. So that means I put the divider here. So in the leftmost space, this corresponds to how many 1 rupee coins I have chosen. Now I have not chosen any 2 rupee coins. So that means let me put the divider right here. Okay, which means this 2 rupee coin space is empty. I have not chosen any 2 rupee coins. Now I've chosen 1 5 rupee coin. So this was supposed to be the 5 rupee coin box. This is the 10 rupee coin box. So now this is my picture. I have 1 dot, 2 dividers, 1 dot, 1 divider, 1 dot. Okay, and so on. So the point is, every possible picture that you can draw in which you have 3 dividers and 3 dots, that always corresponds to some choice of coins. Okay, so let's see if we understand this correctly. So suppose I have one divider. So it starts with a divider, let's say, and then I have this followed by this. So here is a picture with 3 dividers and 3 dots. What choice does this correspond to?
Six choose to 3.
Sorry, what? No, I'm not asking how many possibilities there are. What I'm asking is, this
2
is
to
a
5.
pictorial encoding of a certain choice of coins, right? I chose some number of 1 rupee coins, some number of 2 rupee coins, and so on. So I want to know if this was the picture I got, then what must have what must I have chosen? What were my coins?
2 to 5.
0 1 rupee coin. 2
No
5.
one. Okay, wonderful. No 1 rupee coins. Then
2 5 2 rupee coin.
2 rupee coins. So I chose 2
1
rupee
5
coin,
rupee coin.
1 5 rupee coin,
0 10 rupee coin.
0 10 rupee coins. Okay. So I just have to see in which compartment the dots are. Right. Okay, great. So now let's answer the question that we just answered, which is how many different configurations of dots and dividers can I have? Right. So the number of pictures that I can draw. So this is the number of configurations of 3 dots and 3 dividers. Well, what is that? This is something that we just said, right? 6 factorial by 3 factorial, 3 factorial, if you wish. If you think in terms of, I have 6 objects and 3 of them are alike, another 3 are alike, then, I first permute all 6 and then permute these 3 amongst themselves and those 3 amongst themselves. Or, like we just said, you can also think of it as, I have 6 positions, I have to choose 3. I'll put the dots in those 3 and I'll put the dividers in the rest. Okay. So this is 6 choose 3 in this example. And more generally, so if you sort of see what this dots and dividers business is, it's like asking, so suppose I have, so here's yet another reformulation of this problem. Okay, so I have, this is the balls and boxes problem. So I have boxes. Okay, so I have n labeled boxes. So it's 1, 2, 3, 4 till n. So the boxes are all different because they all have labels on them. I know I can distinguish the boxes. So n labeled boxes are given, and I want to put r identical balls into these boxes. Okay, n labeled boxes, number of ways of putting r identical balls. So how many ways are there of putting r identical balls?
N plus R minus 1 choose to R.
Okay, why is that?
So similarly, x1 plus x2 plus xn, that is equal to R. In that
Okay.
case.
Right, absolutely. So this is actually a version of the same problem. Okay, and this dots and dividers is exactly what will help us. See, there are r identical balls. So each ball you first think of as a dot. So there are r dots now. But how the balls are to be distributed amongst the boxes, that I will prescribe by putting dividers in the appropriate places, right? So, so the first divider that I put, so if depending on how many balls there are in the first box, so if there are 2 balls in the first box, I'll put the divider after the first 2 balls. If there are no balls in the second box, let's say second box is empty, then I'll put the divider immediately there. Okay, there is say only 1 ball here. Let's draw a configuration. If there are 2 balls, no balls, 1 ball, then I put a divider here, and so on. Okay, so if this has 3 balls, then I will take 3 dots and then put the divider, etc. Okay, so the number of ways of putting r identical balls into n labeled boxes, so let's call it n labeled boxes, can be reformulated as the number of dot and divider configurations, number of dot and divider diagrams with how many dots and how many dividers? with how many dots should I say? With dash dots and dash dividers.
R minus
minus
1.
Yes. N
minus 1 dividers.
N minus 1 dividers, because there are N boxes, right? So the dividers are separating the boxes here. That is N minus 1. Dots is R, because there are R balls. Okay. And now this is, what did we say? Total now, total dots and dividers, there are N minus 1 plus R total. That factorial divided by N minus 1 dividers mutually permuted, R balls mutually permuted. Okay, so it's N minus 1 plus R factorial by N minus 1 factorial R factorial. And that's exactly N minus 1 plus R, choose R. Which is also the same as N minus 1 plus R, choose N minus 1. Okay, so there is a slight asymmetry here between balls and boxes. You have to be a little careful. So the top is N minus 1 plus R. So it's like N plus R minus 1. So if I change N and R, the sense that if I ask how many ways are there of putting N identical balls into R labeled boxes, okay, then the answer is not the same. Okay, the answer is slightly different. The thing on top is the same. I reverse the roles of N and R. The top becomes N plus R minus 1, still the same. But then the thing on the bottom of the C is choose N now. Whereas in the original case, it was that same thing on top, choose N minus 1. Okay, so there's a slight asymmetry between balls and boxes. If I interchange the numbers of balls and boxes, you won't get the same answer. Okay, so so that's the thing about let's see, what was it? Combinations with repetitions. Okay, great. And of course, the very same problem can come up in many different avatars. So here's another question which is very closely allied to this. How many non-negative integral solutions are there to the following equation? How many solutions to the equation x1 plus x2 plus x3 plus x4 equals 50? But not just non-negative integral solutions. So if I say xi's have to be at least 1 for all I, and they're all integers. See, earlier it was 0 was allowed, right? So I say each xi should be at least 1.
Introduce new variable y equal to xi minus 1.
Wonderful. Okay, so let me make it slightly more exciting. So suppose I say x1 is greater than or equal to 1, x2 is at least 2, x3 is at least 3, x4 is at least 4. So I put some constraints on the variables. Okay, now what should I do?
y1 equal to x1 minus 1.
Okay, wonderful. So the nice way to do this is to introduce new variables. See, the point is, in order to solve the original problem, I have to be, I should allow values from 0 onwards. Only then it's really a combination with repetitions products. In other words, see, this original problem is the one I know how to solve. Okay, so I have to keep this as my primary assumption. Then I can solve the problem. So the goal here is to reduce it to that case. So you introduce new variables, y1 to be x1 minus 1, y2 to be x2 minus 2. And now the nice thing is all the yi's are therefore just greater than or equal to 0. But the original equation may change, right? So it's now y1 plus y2 plus y3 plus y4 equals
40.
That's 10 less, right? 40. Okay. So having done this, now I go back and solve the problem. So what is this? What is the solution to this? How many balls and boxes do I have? I have 40 balls to be distributed among 4 boxes. Okay, so 40 balls plus 4 minus 1, 3 dividers. Okay, and from that I must choose the position for the 40 balls. Okay, once I do that, the dividers are fixed. So this is 43, choose 40, or 43, C 40. So I have those many solutions. Okay, so this is one way of saying the same thing. So now let's see what else one can do with this. So I mean, another maybe one last equivalent version of this is again in terms of monomials. So here's a question: how many distinct monomials of degree D are there in n variables? So if I construct polynomials in n variables, let's say, okay, so I have x1, x2, x3 like that till xn, and I look at all possible, not polynomials, monomials. So monomial is just of the form x1 raised to some power, x2 raised to some power, and so on. Right? Now the question is, how many distinct monomials of degree D are there in n variables? Okay, so notice that this sort of came up in what we just did regarding the multinomial theorem and so on. So we said, suppose I take these n monomials, x1 plus x2 plus xn, raise the whole thing to the power d, then what is this going to become? It's going to become a massive sum, and the sum is going to be the following. It is, I have d is the total degree. Choose, there'll be some multinomial coefficient, right? a1, a2, an, x1 power a1, x2 power a2, xn power an. Okay, where what are the AIs? So I should take all possible ordered n tuples a1, a2, an. AIs can be greater than or equal to 0, but the point is the sum of the AIs is the degree, is this power d that I have. Okay, so recall, this is exactly the multinomial situation that we talked about, right? If you have n variables, you take their sum, you raise it to some power, it will expand out, and the coefficients will be multinomial coefficients, and all the terms that you get will be monomials of degree d. Okay, but the question I'm asking is not about the coefficients now. Okay, so now I want to ask, how many different monomials will there be in this sum? When you expand this out fully, how many different possible monomials will you get? So that's the question. How many distinct monomials of degree d are there?
In a1 plus a2 plus extra an equal to d.
Absolutely. So observe, it's just the same problem in disguise, right? Because what is really happening here? It's just, well, you can already see it here. It's just the number of ordered tuples a1, a2, an satisfying the very two same conditions, that their total sum should be d and each of them should be greater than or equal to 0. Okay. So the answer therefore is similar. So the number of distinct monomials is like saying total is d. So there are like d balls and there are n boxes into which I must distribute them. So d plus n minus 1, choose d. In the other notation is this. So there are those many monomials that will appear when you expand out. Okay. And of course, we know something more here. When you expand, I mean, the coefficient of a given monomial, we know what it is in terms of the binomial coefficient. Okay, great. So that's the situation with, so this was what we said, all these combination with repetition problems can be thought of as the following balls and boxes problem. I have n distinguishable boxes. So the boxes are labeled, but the balls are not. So this is boxes are labeled or distinguishable. Okay. The balls are not. Okay. Now there are all these other possible combinations. What if the boxes are labeled and the balls are also labeled? Okay. Or what if the balls are labeled, but the boxes are not labeled. Okay. And finally, what if both of them are not labeled? Okay. So let's consider each of them in turn slowly. So this whole business of labeling versus not labeling it can be rather confusing, and it's probably not useful to remember formulas based on is this labeled, that not labeled, then you have to use a particular formula. That sort of thing is probably not a good idea, because one might get confused very easily. So the best thing is to sort of just rethink it from first principles. What exactly are you doing? What are you trying to count? And how should one do it? So one case we have done. Okay, that's the combinations with repetitions. So now let's do the other next case. So suppose I say I have n boxes. The boxes are labeled and the balls are also labeled. So what does this mean? I now have n boxes, 1, 2, 3 till n. And I have to distribute within this n balls, which also come with labels. I mean, not n, r. Okay. So I have n labeled balls, sorry, r labeled balls to be distributed among n labeled boxes. So everything is distinguishable. That's the point. So it's not like if I put 2 balls in the first and 1 ball in the second, it depends on which balls I put. If I put balls 1 and 2 here and ball 3 here, then that is different from the configuration in which I put balls 1 and 4 here and ball 7 here, for example. Okay, so the actual ball that is there in any given box, that matters. I will consider 2 configurations as different, or rather I will consider 2 configurations as the same only if each box number k, contains the exact same labeled balls. Otherwise, even if they differ, any one box has one ball which is different, I will think of it as a different configuration. So is the question clear? I mean, it's already, if one explains it too much in words, I get confused myself. So how many different configurations are there? The balls are also labeled, the boxes are also labeled. So any suggestions? I mean, how would you start thinking about it? So one thing is, unlike the earlier case, let's not look at it from the point of view of the boxes. When you don't start thinking of the boxes. Sorry, what?
If I'm taking the first ball.
Okay, very good.
That ball having the n choices.
Okay, great. So you just have to look at it from the point of view of the balls, not from the point of view of the boxes. So let me just do what you're saying as follows. So take a ball 1, and that ball has to go to some box, right? This ball is going to be placed inside some box. So take the second ball, that ball has to go to some box. Third ball has to go to some box, and so on. So what is it really? It's actually a function. The number of such configurations is the same as the number of functions from the set comprising 1 through r to the set 1 to n. Is that fair? Is it clear why these are the same? Just take each ball. You need to know where that ball goes, right? So if I give you a function like this from this set 1 to r to the set 1 to n, then that determines a configuration. It tells you where to put each ball. Okay. But of course, counting is easier. What's the count? How many functions are there, or how many balls in boxes are there? So first ball had n choices. It could go into any one of the n boxes. Second ball,
n choices again.
N choices again, and so on. In fact, all of them have n choices. So n into n, which is n power r. Right? So I mean, we've seen this sort of thing before, right? This n power r thing keeps occurring, right? Okay, good. So that was we have also seen this therefore earlier. This both labeled case is the easiest actually. Very good. So let's see, what have we done? Both are labeled, then we know what to do. If balls are not labeled, but boxes are labeled, that's still fine. We have this clever divider idea. By the way, it's a rather clever idea, this whole divider business, to count these configurations. Now, the other two cases are remarkably harder actually. So let's say the what's left, by the way, boxes, balls. So the boxes are not labeled. Okay, so they are all identical boxes. The boxes all look the same, but the balls are labeled. So what does this mean? I have, let's say some number of balls. Let's say 1, 2, 3, 4. There are 4 balls. Okay, let's say I have R labeled balls, which I need to distribute among n boxes, but the n boxes themselves are not labeled. I don't care, they are not in any order. The boxes don't appear in any order. So for example, I could, so what matters to me is only the following. I could take the balls 1 and 2 and put them into one box. So these two go into one box. Okay. Ball 3 goes into a box by itself. Okay? And maybe ball 4 goes into a box by itself. So this is the information I want to keep. Okay? This is how I have put them. These 3 boxes that I have drawn, I don't care about the order of the boxes. I'm not permuting those boxes or anything. So the only information I want to remember is which balls came together to form one group. Okay. So this is one possible configuration that I'm talking about of distributing these 4 labeled boxes into 3 boxes here, for example. 4 labeled balls into 3 boxes. So what would be another way of doing it? I could put the balls 1 and 1, 2, and 3 together into one single box. I could put 4 into a box and I could keep the last box empty. So you can think of this as another way of dividing these into 3 boxes. Okay, one box is empty, one box has 1, 2, 3, another has 4, and so on. So you can keep, you can actually write down many of these configurations, and it's sort of much harder to count. It's not as easy to count as the earlier 2 cases. I mean, combinations with repetitions is already the hardest that we have seen so far. This is definitely harder than that. Okay. So this problem, by the way, is sometimes called the set partition problem. An equivalent version of stating this is to say, I want to partition a set. Okay, and I want to know how many different ways there are of partitioning a set. So what is a set partition? So you've probably seen, equivalence classes and so on. So suppose I have 7. Let me take the 7 numbers 1, 2, 3, 4, 5, 6, 7, and so let me do the following. So I will I will partition this set. What does partition now mean? Partition means I put them into blocks. So for example, like equivalence classes, if you wish. So 1 and 3 are in one block. 6 and 7 are together. 5 is together. 4 and 2 are together. Okay, so imagine this is a way of putting them into boxes. Right? These are the 4 boxes. 1, 3 in one box, 6, 7 in one box, 2, 4 in one box, 5 in one box. Okay, but the order of the boxes doesn't matter. This is how I have divided. So this is a set. Such a thing is called a set partition. So a set partition is just a way of it's a collection of pairwise disjoint subsets of your set whose union is the whole. Okay, so that's called a set partition. So now you can write many other set partitions. So for example, let's take this again. and let's partition it as, so instead of, I can put 1, 2 together, 4, 5, 6, 7 together. Maybe I'll keep 4 boxes. So here is another set partition, right? And so on. So we can just keep drawing these guys. 1 by itself, 4 by itself, 6 by itself, and the remaining fellows. Okay, and so on, etc. So there are lots of such things that you can draw. So this is the problem of set partitions. And the count, the number of ways of doing this, we have a name for it. So let's denote it like this. It's S of n comma r. So what is this? This is the number of set partitions of the set 1 to n into r non-empty subsets. So I don't want empties. I mean, when I first described, I said, oh, some boxes I can take them to be empty. But finding out, the number where, allowing empty, that can be determined from the cases where you don't allow the empty. Okay. So somehow this is not a big deal. You can forget about allowing empty boxes. Let's assume that you have to take R balls and you fill it into n boxes, and none of the boxes should be empty. You have to fill all the boxes, at least one ball in every box. That is what this number S and R counts. It's a number of set partitions of the numbers 1 through n into R non-empty pairwise disjoint subsets. Set partition already means that. So non-empty subsets. So for example, the ones that are here on this diagram are, these are all partitions of 7 into 4 blocks. Okay? Sometimes we call these blocks. So 1, 2, 3, 4, 1, 2, 3, 4. So and there are many more. So this number is there is no very easy closed form formula and so on. It's a very important number. It's called the Stirling number. Of the second kind. Okay, there is also a Stirling number of the first kind. So this is called the Stirling number of the second kind. Okay, and so since we are sort of talking about Stirling numbers, let me also tell you what the Stirling number of the first kind is. And that's actually, so let's put small s for that, SNR. That's something which, it's surprisingly easy to, it's something that really should have come up in everything that you have done until now, especially with talking about groups and so on, permutation groups. So SNR is the following. It's the number of permutations in Sn, in the group Sn, symmetric group, with exactly R cycles. Whose cycle decomposition contains R cycles. Whose cycle. So when I say R cycles, I will also count all the singletons, by the way, whose cycle decomposition contains exactly R cycles. Okay, so this is called the Stirling, this number is the Stirling number of the first kind. So just to give you an example, if you take n is 7 or something, so inside the group S7, what are the, what's an example for permutation which has, say, 4 cycles? So let's do this very same example. I have 7 guys here, but so let's take the last one, 1, 3, 6. Maybe not the last one, this one here. Let's take the second example. So that's the Stirling number of the second kind, but let me construct for you a similar example for cycles. So I can take 1, 2, 3, 6, 4, 5, 7, 3, 6. So here, for example, here is a permutation of S in S7, which has exactly 4 cycles in its cycle decomposition. So it permutes 1 and 2, it leaves 3 fixed, 6 fixed, and it cyclically permutes 4, 5, 7 in this order. Okay, but observe, this is, however, this and the previous one are not the same problem. It's, if I divide the set 1 to 7 in 4 blocks, that will determine many different permutations with the same cycle structure. So for example, observe this 4, 5, 7 is one possibility, but I could also look at 4, 7, 5. I can arrange those last three numbers to form the inverse cycle. Okay, so these are of course not equal to each other. I get two different permutations whose block structure is the same, which divides the numbers into the same blocks. Okay, so you can already imagine. So which one do you think is bigger, a small SNR or capital SNR? Which of these two counts is going to be larger? The number of permutations with R cycles or the number of set partitions with R blocks?
Small SNR is bigger.
Small SNR is bigger because, to each.
The capital SNR is just a partition, but small SNR there is something.
There is something meaning. There is what? What are you doing?
We can change the elements. That's why.
Correct. So to each partition, you take an underlying partition. From that partition, you can form multiple permutations. There are many permutations that will typically correspond to a given partition, right? Like the one we just did. You can cyclically permute those things in many ways. So in fact, how many different ways there are. See, if a block has 3 elements, you can form 2 factorial permutations from it. Right? In general, if a block contains k elements, right, how many ways are there of cyclically permuting a set of k elements? There are k minus 1 factorial permutations that you can form from just that very same set of k elements. So you will expect that this little SNR is in general going to be bigger than capital SNR. Okay, good. So this is the, these are examples of the, these are slightly harder problems. And so maybe next time I'll talk a little bit about generating functions and so on. And hopefully we'll see some ways of computing these numbers in terms of generating functions. Okay. But it's already interesting that, an easy question or easy sounding question like this, you would imagine that this is the most natural question you would think of. Since we know cycle decomposition, I'll tell you how many cycles I want. Can you tell me how many permutations there will be? Okay, so even that question is not all that straightforward. Okay, so that's one. And then finally, again something that maybe I will come to next time is the last of the lot. So boxes, balls. If the boxes are unlabeled and the balls are unlabeled, meaning the boxes are also not distinguishable, the balls are also not distinguishable. So what does that mean? Going back to the same setting, suppose I have R balls, they're not distinguishable. So I'll just put dots for them. I don't put labels on the dots. So here's a collection of how many? 1, 2, 3, 4, 5, 6, 7, 8. 8 dots. And the boxes are also not distinguishable. What does that mean? So maybe I'll put them into boxes in this manner. Okay, so here's one way of dividing these 8 balls into 3 boxes. But let's do the same thing here. Let me look at another way of dividing these boxes. So instead of these blue lines, I will divide them in this way. Okay, so here are 2 possible divisions of these 8 boxes into 8 balls into 3 boxes. Are these different or the same division?
Same only.
Same, why?
No labeled, so.
Correct. So it's not labeled, but why do you say they're the same?
Boxes are also not labeled, so both comes.
So 2 boxes contain same number of balls and the remaining 2 balls.
Correct. So if you see what matters finally for, when are they different or rather when are they same, if you have firstly the same number of boxes and the number of balls in the boxes is also same. right? So here you can represent this by saying, oh, one ball has 3, another ball has 3, and another ball has, sorry, another one box has 3, another box has 3, and another box has 2. And well, this is the same guy, right? It's just that I have a different set of 3 balls and have been put into the boxes, but I don't want to distinguish between those. So both are really the same. They're both 3 plus 3 plus 2. Okay? And these are what are called integer partitions. So this final category where I don't care about balls or boxes being labeled, that is the problem not of set partitions. So remember, the previous one was set partitions. This is what are called integer partitions. So it's like saying, I want to know in how many ways can I write 8 as a sum of 3 different numbers. I mean, not 3 different numbers, of 3 numbers. Okay. And this is what's usually called, this is a very famous number theoretic function. So it's called the partition function. So P of n is the total number of partitions of n without any restrictions. And you can also talk about P of n comma r, which is the number of partitions of the number n into r non-zero parts. So this is like our earlier example where with set partition. So we want r boxes and every box should have at least one dot. Okay, that's what this r non-zero parts means. And again, something I'll do next time, but here are the first few partitions. So one, if I take n equals 1, you can only partition it in one way, okay, just as itself. If n is 2, then there are 2 possible ways. You can put both balls into one single box, or you can put the balls into 2 different boxes. So if n equals 3, you can put all 3 into one box. 4 becomes 3 plus 1, 2 plus 2, and so on. Okay. So this is now I'm allowing all possible numbers of boxes also. And this function is sort of even harder. I mean, you can't. It's maybe one step of complexity higher than even the Stirling numbers in some sense. So the generating function is it's a more complicated generating function here, if you wish. I mean, or more simple, depending on your point of view. But again, this is work of Ramanujan, who studied this intensively, and there is actually an exact formula even for this number P of n. Okay? Not a very easy to state formula, but this is what's called the Hardy-Ramanujan Rademacher formula for the total number of partitions. Okay, so anyway, so my plan for my last lecture next week is to sort of talk about generating functions, which sort of gives us some way of understanding these last 2 cases. So what are generating functions and how does that enable us to understand the partition function as well as the Stirling numbers? Okay, but for today I'll stop.
So, okay, so thank you.
Yeah, thanks.
Participants, is there any query you can ask? Otherwise,
yeah, feel free to ask if you have questions. Okay, if not, there'll be a tutorial tomorrow anyway. So I will sort of send out that, yeah.
Okay, so thank you, sir.
Thank you, madam.